Calculus is the mathematics of change. In this video, we are going to show you how to use calculus in industrial and real-life engineering problems involving several quantities that are changing simultaneously with respect to time. Here's our problem for today. A tank containing 100 liters of a brine solution initially has 4 kilograms of salt dissolved in the solution. At time equals 0, another brine solution flows into the tank at the rate of 2 liters per minute. The brine solution contains a concentration of 0.5 kilograms per liter of salt. At the same time, a stopcock is opened at the bottom of the tank, allowing the combined solution to flow at a rate of 2 liters per minute so that the level of liquid in the tank remains constant. Number 1. Find the amount of salt in the tank as a function of time measured in minutes. Number 2. Find the limiting amount of salt in the tank, assuming that the solution in the tank is well mixed at all times. And number 3. Find the amount of salt in the tank after 10 minutes, 30 minutes, 60 minutes, 3 hours, and 24 hours. Let's analyze this problem. So what we have here is a tank, and the tank contains 100 liters of brine solution. So the amount of liquid in this tank is 100 liters. Initially, this tank contains 4 kilograms of salt. So that means the amount of salt in the tank initially is 4 kilograms out of the 100 liter solution. In other words, there are 0.04 kilograms of salt per liter of this liquid. Then there is an inflow of another brine solution that contains 4 kilograms of salt for every liter. And the rate of inflow is 2 liters per minute. So the inflow is 2 liters per minute. And the concentration of this brine solution that is flowing into the tank is 0.5 kilogram of salt for every liter, which we can now simplify as 2 times 0.05 is 1 kilogram of salt for every minute. However, at time equals 0, right at the moment that there is an inflow of this brine solution into the tank, the stopgap cock is also opened, allowing the liquid to overflow at the same rate as the inflow. So the outflow rate is 2 liters per minute. So if 2 liters are coming into the tank, there are also 2 liters of liquid that is coming out of the tank. So that means the amount of liquid in the tank would remain constant at 100 liters. What is changing is the concentration of the salt. Because initially, you have this concentration of 0.04 kilogram for every liter of liquid, but now you are adding 1 kilogram of salt for every minute. So at the start, you have just this 0.04 kilograms of salt initially. But after 1 minute, you would be adding 1 kilogram on top of what is already inside. You are also letting the liquid out. So part of this 0.04 kilograms of salt is also flowing out of the tank. We need now a function that will track the amount of salt that is flowing out of the tank as a function of time. Because every minute, the concentration of the salt here changes. Because you have here a concentration that contains more salt than what is inside the tank. And therefore, every time this new brine solution is added into the content inside the tank, since there is equal amount of liquid that is flowing out of the tank, then the concentration of the salt here would just keep on increasing until some limiting value, which is what we are trying to find in number 2. So in number 1, we want to find first what is a function that can compute for the amount of salt in the tank. And in number 2, we want to find what is the limiting amount of salt inside the tank. And in number 3, we are going to compute the amount of salt in the tank by substituting this value of time for whatever equation we arrive at in problem number 1. So that's our analysis for this problem. So let's begin solving now this problem. First, let's define our function u of t to be equal to the amount of salt in kilograms in the tank as a function of time. So think of u as the amount of salt in the tank. And the amount of salt in the tank varies with respect to time. We start at time equals 0 with an initial value of 4 kilograms of salt out of the 100 liters liquid in the tank, and as time passes by, the amount of salt concentrated in this solution increases. Then we define the derivative of u with respect to time to represent the rate at which the amount of salt in the tank changes as a function of time. So for an infinitesimal change in time, there is also a change in the amount of salt. At time equals 0, we know that there are 4 kilograms of salt present in the tank. That is given in the problem. Now, we can now define du over dt, which is the rate at which the amount of salt in the tank changes, as the salt inflow rate minus the salt outflow rate. This means the amount of salt that is coming in the tank minus the amount of salt that is going out of the tank. We can represent now the salt inflow rate using what is given in the problem. The inflow rate is 2 liters per minute, the outflow rate is also 2 liters per minute, and we maintain the 100 liters of liquid in the tank. But for the amount of salt in the inflow, there is 0.5 kilograms for every liter, and the amount of salt that is flowing out of the tank is represented as a function u of t, which is the amount of salt in the tank for every t value out of the entire content of the tank, which is 100 liters. We can now simplify this by canceling out L and L here. The unit of U is the amount of salt in kilograms, so this is U kilogram per 100 liter. And 2 times 0.5 is 1, the unit is kilogram per minute. And at the right side, common factor is 2, so you have 1 here. This becomes 50. So we have U kilograms over 50 minutes. So this becomes 1 kilogram per minute minus U over 50 kilogram per minute. That is equal to du over dt. Let's write this clearly. So this is now our result. Then in our computation, let's just remove the units, kilogram over minute, and we have now this equation. Du over dt is equal to 1 minus u over 50. Now this u means u of t. Then we can write this as one fraction. So our LCD is 50. 50 divided by 1 is 50 times 1 is 50. 50 divided by 50 is 1 times u is u. So we arrive now at this equation representing du over dt. Now we want to solve for u, but we have an equation that contains a derivative. This is a first order differential equation. And in order to solve this equation, we are going to use the technique separation of variables. You have the variable u here. We want all the u's to be at the left side and all the other variables at the right side. So instead of thinking of d over dt as an operation on the variable u, we now think of du over dt as a fraction, and therefore multiplying both sides by dt over 50 minus u, we arrive at this equation. And then we can now take the antiderivative of both sides to arrive at this equation. Let's go to the next page and solve this equation. What is the antiderivative of du over 50 minus u? Its antiderivative is negative ln of the absolute value of 50 minus u, and the antiderivative of dt over 50 is equal to t over 50 plus c. And then let's divide both sides by negative 1 to eliminate this negative sign before ln. Then to do away ln, let's take the exponentials of both sides, meaning we raise the natural number e to this left side expression as the exponent, and we do the same thing at the right side. And so we now arrive at e raised to ln of the absolute value of 50 minus u equals e raised to negative t over 50 minus c. Then the left side contains inverse functions. E and ln e cancel each other out, so what's left at the left side is the exponent absolute value of 50 minus u. And then, using property of exponent, we can now rewrite the right side as e raised to negative t over 50 times e raised to negative c. And e raised to negative c is just another constant And let's call that other constant as C sub 1. Now, since C sub 1 could be positive or negative, then we can just remove this absolute value notation to arrive at 50 minus U equals C sub 1 times E raised to negative T over 50. Let's go to the next page and solve for U. So by rearranging, we arrive at U equals 50 minus C sub 1 times E raised to negative T over 50. Now this U means U of T. That's the function U of T. This form is almost the answer for our first question. The only problem is we still do not know what is C sub 1. But we know the initial value that at T equals 0, U of T is equal to 4. So using this initial value, we now arrive at U of 0 equals the right side of this equation with T replaced by 0. And this must be equal to 4. Simplifying, we arrive at 50 minus 4 equals C sub 1. And therefore, C sub 1 is equal to 46. Now, knowing what's the value of C sub 1, we can now replace this C sub 1 by 46. And so we now arrive at a function that is our answer for problem number 1. The amount of salt in the tank as a function of time is now represented by 50 minus 46 times E raised to negative T over 50 with 46 as our C sub 1. This is now the function that we are going to use to answer our problem number 3. But before we go to problem number 3, let's now go to the second question. Find the limiting amount of salt in the tank. That means, as time approaches infinity, what is the maximum amount of salt in kilograms in the tank? So let's compute now for that limit. So we write the limit of U of T as T approaches infinity is equal to this right side expression. Now, what happens to E raised to negative T over 50 as T approaches infinity? We can visualize what's happening to this quantity by going back to the graph of E raised to T. So here, the horizontal axis is the time. The vertical axis is the value of Y equals E raised to T. Notice here that as time becomes smaller and smaller, that is, the time is going to negative infinity, the height of this curve is getting closer to the x-axis. And so, the value of this expression as time approaches negative infinity approaches 0 because the y value is approaching 0. So in here, you have E raised to negative T over 50 where T is approaching infinity. And so you have negative infinity over 50, which is basically going to negative infinity. And therefore, this expression becomes basically E raised to negative infinity. And as E is raised to negative infinity, the value of this expression approaches 0. And therefore, this entire part here can just be replaced with 0. So you now have 46 times 0 at this part. 50 minus this expression after the minus sign is equal to 0. And so the limiting value is 50 kilograms. What does this mean? This means that as time approaches infinity, the maximum amount of salt in this tank cannot be more than 50 kilograms. Why is that so? Remember that the volume of liquid in this tank is always 100 liters. And remember that the inflow rate is 2 liters per minute, and this brine solution that is flowing into the tank contains 0.5 kilogram of salt for every liter per minute. So 0.5 kilogram of salt for every liter, that means 1 kilogram of salt for every 2 liters. So the ratio of salt to the total liquid is 1:2. And so if there are 100 liters of liquid in the tank, if the ratio is 1:2, that means the amount of salt is 50 kilograms. And that happens when all the liquid that are initially present here already overflowed, such that essentially the concentration of the salt in the tank is whatever is the concentration of this new brine solution that is flowing into the tank. And that is always 50 kilograms out of 100 liters or 1 kilogram out of 2 liters. So that is the limiting value of the amount of salt in the tank as t approaches positive infinity. Then let's answer now problem number 3. Find the amount of salt in the tank after 10 minutes. So all we have to do is, using the function that we already computed, we just substitute the time for t. And so if t is 10 minutes, we have 50 minus 46e raised to, copy this negative sign, and then replace t by 10 minutes over 50. And that gives us 12.34 kilograms. And for letter B, this gives us a value of 24.75 kilograms. Letter C, after 60 minutes, we have 36.15 kilograms. At time equals 3 hours, that is 3 times 60 equals 180 minutes, the amount of salt in the tank is 48.74 kilograms. And after 24 hours, the amount of salt in the tank is 50 kilograms. And anything beyond 24 hours, you will notice that you will get this limiting value. Now, at what point does the amount of salt reach 50 kilograms? You can compute that by letting this u sub t equals 50 and solve for t. But I will leave that as your exercise to solve for t. So thank you very much, and I hope you now come to appreciate how powerful calculus techniques are in answering real-life problems that regular algebra cannot solve. So thank you, and we hope to see you again in our next video.